All right, good morning.
Good morning.
How are you guys?
Great.
Okay, today we're going to be learning a couple different things. We're going to be learning about, we're going to develop models to show to show atomic structure of elements, and we're going to analyze patterns in the periodic table that show relationships between atomic structure and macroscopic properties. Now, look at some of those words in that second part there. Okay, it says patterns in the periodic table and shows a relationship between atomic structure and macroscopic properties. Okay, you guys, do you recall what I mean by atomic structure? Okay, what is an atom? Do you know the structure of an atom? Let's review a little bit. We did this yesterday. So we have the nucleus. What's found in the nucleus? Are electrons found in the nucleus? Where are they found? Around. Okay, so that's atomic structure. Okay, this is a model of the atom. Obviously, atoms don't look like that, but this is a representation of what an atom could possibly show. Okay. All right. Now, the word macroscopic, it might sound a little bit like the word microscopic because it's basically looking at things. Scope is how we see things. And if we were talking about micro, what would it mean? Small. And macro is the opposite, so it's large things. So obviously atoms are extremely small. We can't see them. Okay? And macroscopic is very large. So basically there's a relationship between the things that we can't see and the things that we can see. Okay? So as we look through the periodic table, there's going to be some things that we're going to talk about that emerge and basically from certain patterns in the periodic table, and these patterns are in some cases related to properties of elements. Okay, so we'll get there eventually. All right, so where are we going to start? We're going to start by looking at our periodic tables and looking at each specific element, and then hopefully by looking through the different elements, some patterns will emerge. Okay, so it's going to be kind of like a discovery of some things as we look through the periodic table. Look at the very first element on the periodic table. It's hydrogen. Okay, so on your chart, write out the word hydrogen, and then the symbol is what? H, okay? The atomic number, let me draw a little picture here for us. Here's hydrogen. It has this number up here, and then there's a smaller or a different number, not smaller, 1.0079. This first top number is the atomic number. Okay, make notes of this, please. Now the atomic number you learned yesterday when we did the history of the periodic table, the little worksheet with the fill in the blanks that we did and the questions that, girls, the questions that were at the end, we answered those. We learned what atomic number is. What is it? Which of the subatomic particles does it represent? Raise your hands. Donovan? The number of protons. So it's equal to the number of protons. Is there another number that it's equal to? Andres? It's not the neutrons, it's the electrons, okay? So the number of protons and the number of electrons is always going to be the same, okay? So it's also equal to the number of electrons. This number at the bottom is the mass number, or we can also call it the atomic mass. Okay, and I'll tell you how that number is determined in a moment. okay? So the atomic number for hydrogen, what is it?
1.008.
And how many protons does it have?
1.
And how many electrons?
1.
And what's its atomic mass?
1.008.
Okay. Now, this number is almost 1, right? Would we agree? It's not almost 2, is it? Okay, it's almost 1. Why isn't it exactly 1? Okay. This number, the atomic mass, is determined, basically it's the mass of the atom. Okay. Every single element is going to have a different mass. Okay. Yes. Is it 1.079? Oh, mine's different than yours. Don't worry about it. It's the same mass, but yours is rounded up 1 decimal place. Okay? And that's not really going to be significant because what we're going to have to do eventually is we're going to have to either round this number down or round this number up. In this case, we'll round it down to 1. Okay? Now, let me get back to what the number represents. It represents the mass of the atom. Okay? So every atom is going to have a mass, and the mass is not determined at all by electrons because electrons don't have any mass, really. Virtually no mass at all. Okay, their mass is completely insignificant. What makes up the mass of the atom then? Everything inside the nucleus. The protons and the neutrons make up the mass of the atom. Okay? Every proton has an atomic mass unit of 1. What did I just say? Every proton has a mass of 1. And every neutron has an atomic mass unit of also 1. So if we add up all the protons and all the neutrons in the nucleus of an element's atom, then we will know its atomic mass. So why isn't this number a whole number? Well, the problem is that there are some elements which have isotopes. Have you ever heard that word before? Okay. Isotopes are variations of an element. Variations of an element. An element's atoms can't vary in the number of protons. For example, if it's hydrogen, its atomic number is 1 because it has 1 protons. That number of protons cannot change. But what can change is the number of neutrons in an atom. For example, hydrogen, hydrogen can have, it's always going to have 1 proton no matter what. But there are actually 3 variations of hydrogen. One has no neutrons. Here's just a little electron up here. This other isotope of hydrogen has 1 neutron. And then a third isotope of hydrogen has 2 neutrons. Okay? They all have the same number of protons and electrons. They only differ in the number of neutrons. So isotopes are variations of an element with different numbers of neutrons. Okay? I think this isotope's called protium, this one's called deuterium, and this one I believe is called tritium. 3 different isotopes of hydrogen. So the cool thing about this is they don't all exist in the same amount in the universe. Can you guess which is the most common one based on this mass number? The first one, very good. This is very, very common. These other 2 are extremely rare. So if you were to average all of the atoms in the universe of hydrogen together, and then you would get this mass number. Okay, does that make sense?
Yeah.
That's why it's not a whole number. just one, okay? Now, moving on, if we know that the mass number is equal to the number of protons plus the number of what? Neutrons. And we already know that hydrogen has one proton, then that means its number of neutrons is going to be 0, right? Basically, every single time that we want to get the number of neutrons, all we have to do is round this up or down. We're going to round it down because obviously it's not 5 or larger. So we're going to round it down to 1. So all we have to do is take 1, which is the atomic mass, minus 1, which is the atomic number, and that gives us the number of neutrons. Make sense?
Yes.
Okay, good. So we have, how many, ooh, I almost wrote it. How many neutrons do we have? 0. Okay. And now we're going to draw the hydrogen that I drew over there, over here in this little box. Everybody should be doing this. Are you doing this? Yeah. Good. No neutrons and one single electron in one energy level. I wrote here orbital. Let's change this to energy level. There is a slight difference between the two. All right, so energy level. There's 1, and how many valence electrons? Well, we don't know what a valence electron is. Maybe we should go over this, okay? A valence electron, you might remember if you did the notes and the presentation for homework last night in your pre-reading. But a valence electron, do you remember? Okay, one moment. So a valence electron is an electron in the outer energy level, or I should say electrons in the outer energy level. Obviously, we only have one energy level here, and in it there's only one electron. So what is the answer? 1. All right? Now we're going to do the same thing for helium, which is the second element on the periodic table. Do you think you can do this on your own already?
No. Yes.
Okay, I'm going to be picking on some of you who don't feel very confident yet. So don't be shy. If you're not sure, I'll give you some extra help. You want some extra help?
I already did.
Look at you.
I told him to do it last time.
Did you really? Okay, here we go. You want some extra help? Or you have a question? I can't hear. Okay, so the energy levels, gentlemen, thank you. The energy levels are just the rings around, basically in the electron cloud outside the nucleus. And I will go about showing you how that works, okay, as we get into the next 2 elements. We're going to do 2 more elements together, and then you'll do the rest of the chart on your own using 4 more elements in order, okay? So, the next element is helium. What's its symbol?
H-E.
What's its atomic number?
2.
And how many protons does it have?
2.
And how many electrons does it have?
2.
Does everybody understand why? If you do not,
I don't understand.
okay, so the atomic number is 2, which is this top number up here, okay? The number of protons is always going to be equal to that number.
Oh, how?
It's just always equal to that number, okay? In other words, the atomic number is defined by the number of protons in the nucleus, okay? Does that make sense to you?
Yeah.
So if you read through from left to right, hydrogen has an atomic number of 1, helium has an atomic number of 2. Then you go down to the next line, lithium is 3, beryllium is 4, boron is 5. They're not just ordered in, chronologically. They actually have that number of protons. Okay, make sense?
Yeah.
So also, Maurice, the number of electrons is equal to that number of protons. Okay.
Okay.
All right. Now, what's the mass number or atomic mass? Leanne.
Mass is 4.003.
4.003. And are we going to round that down or up?
Down.
Down. Okay. So, who would like to tell us what the number of neutrons is and how you go about making that calculation? I think I would really like to hear from Kaiten today. Kaiten, are you with me?
I'm writing it down.
All right, I'll give you a second.
I think I need more than this.
So, got it? All right, look here. This is the atomic mass. This is the atomic number. Can you tell us how many neutrons we have?
2.
2. And how did you come to that calculation? How'd you get that answer? Shh. Do you know? Okay, pay attention. And anybody else who doesn't know how we got that answer, you need to know. So pay attention, okay? You get that answer from the mass number, subtract from the mass number the atomic number. Okay, why? Because this number is equal to protons and neutrons. This number is equal to protons. So if you take protons and neutrons and subtract protons, you're left with neutrons. Make sense? All right, so the number is 2.
Was it the same for the first one?
Did you subtract 1 from 1 from 1? Yeah. That's how we do it every single time, okay? Now, over here, we're going to make our drawing. How many protons?
2.
Where do they go?
In the circle.
Which part of the circle? The nucleus. Okay. 2 protons. How many neutrons?
2.
2. And then we have how many electrons?
2.
Okay. Here's a clue for our question, a question that actually Ferticia asked a moment ago. I think it was, yeah, Ferticia. Yeah. So Ferticia asked, how do we know how many energy levels? So basically, here's a rule. You have to memorize this. There's no getting around it. The first energy level holds up to 2 electrons, okay? The other rule that we're going to get around to in a minute is that the second energy level holds up to 8 electrons, okay? No more. Then when you get into other elements further along, they have differing amounts. I'll let you guys wait until you're in high school biology to learn some of that stuff, okay? If you want to enrich yourselves now, you can. I'll show you some interesting resources where you can learn that, okay? Now, so where are we at? We need to identify how many energy levels there are here. There's only 1, and how many electrons are in it?
1.
And yes, that is our, whoops, there's 2. You guys tricked me. All right. So there's 2. What would happen if there was another electron? Where would we put it? Could it fit in that ring? No, we just learned it only holds up to 2.
You make another.
We'd have to make another ring. And that's how we know how many energy levels there are. Okay? There are some tricks you're going to learn as we get a little bit further along. You're going to see some patterns in the periodic table that are going to make this a little bit easier. Okay? So, here's the third element. What is it? Lithium. And what's its symbol? Li. And what is its atomic number? And from this point, please don't talk out anymore. I will call on you, okay? Because I want to pick and choose some people to contribute. What is the atomic mass? Gerdwins.
6.94.
Are we going to round that up or down?
Up.
2.
7.
Okay, and what is the number of protons? Jude's 3, and electrons, Renzo?
3.
And what about number of neutrons, Sierra? Do you know how to get the number? No? I'm glad I chose you. All right, so this number is 7, which is the mass number. From it, you subtract the atomic number, which is 3. So it's 4 neutrons, all right? Remember, this number is equal to protons plus neutrons. This number is equal to protons. So if you subtract from this number the protons, you're left with only neutrons. Make sense? All right. Anybody else struggling with that? Anybody else struggling with that?
No.
Okay, yes.
Is it okay if you, because you rounded it to 7, if you didn't round it, you put 3, is that okay?
You have to round it, okay? We're gonna go for the number of neutrons in the most common isotope of that element. Now, if you guys understand how we got this 4, give me a thumbs up. Okay, good. Now, we need to make a little drawing of lithium. So how many protons go in the nucleus? Raise your hand. Ahmad?
3.
3. Those are protons. We said it.
Oh.
Electrons. Okay? I'm glad you brought that up. That whenever somebody has like a little bit of unsureness about something like that, it brings up probably some of the same problems other students are having. How many neutrons?
4.
4. Where do they go?
Outside.
In the nucleus, okay? What about electrons? Raise your hand. Ruby. How many electrons in the first energy level for lithium? Lithium has a total of 3 electrons. How many are we going to put in the first energy level? What's the total number we can put in the first energy level that we wrote into our notes? Right here. 2. So how many are we going to put in the first energy level? 2. Ruby, how many does that leave for the second energy level? 1. Good. So we put 2 in the first energy level. We need a total of 3. We need that next one right there. Okay? There's a total of 3. Excellent. Now, you have a question? No? All right. How many more electrons could potentially fit in that electron or in that energy level?
7.
7 more. Okay? So as you go through these, you should be able to fit the rest of them in that second energy level because you're only going to do 4 more. How many energy levels did we use?
2.
How many electrons in the valence?
1.
Only 1 in the valence. Remember, the valence is what, Kaiten? Yeah, what is the valence? Can you see okay? You should get in the front row. You should get in the front row.
Right here?
Yeah.
Sorry.
There is only, before you move, there's only 1 electron in this outer ring. See that? This outer ring only has 1 electron. The outer ring is only going to have, it's going to have all the valence electrons. In other words, the valence electrons are the electrons in the outer energy level. Okay? So these 2 inner electrons that are in this ring, they don't count as valence electrons. We only count the ones in the outer ring. Okay? So there's 1 valence electron. Okay?
Got it.
All right. I want you guys to complete the chart on your own. I'm going to come around and check on you, and if I see you're struggling with something, we'll work on it together, okay? How many of you feel confident that you can do everything alone? Okay. If you feel less confident, I'll get you into a group and we'll work on it some more, okay? That'll be our group work, and then if I see any of you need some individualized instruction, I'll work with you as well. Okay. Anybody who thinks they need some extra help, we're gonna meet back at this back table for a little bit. So, Andres, anybody else, come on over here, bring a chair. Don't be shy. Some of us have a hard time paying attention, I know. You wanna join us, Ruby? If you wanna turn around or sit next to somebody and work with each other, that's fine, but don't be talking across the room, please. Come join them if you want. Join us.
Bless you.
Alright, so, so we're on this next one, beryllium. And did you already fill that in? That stuff, okay, so. So you have the mass number. How many number, what's the number of protons for this for beryllium? What's at the top? Okay, so it has 4 protons, over there, and how many electrons? How do we figure out who guys have ones? That's for neutrons, what about for electrons? Yes, no, for electrons and protons are always on the same, can you see that? Okay, so the one that you subtract is for neutrons. 9 is the mass, right? 4 is the atomic number, so it's 9 minus 4 equals 5. Put it in, and then we're gonna divide it, okay? We have 1, 2, 3, 4 protons, right? And how many neutrons did we just say? 5 neutrons. And then what's the ratio? Four electrons total, but how many are in first? 2, and that leaves 2 more. You know why there's only 2 Yeah. So we need the number of energy levels, how many are there? And how many vacancies? Let's see if we can do one alone. Now what's your guys'? What for? Your water? Wait. I still have something we need to talk about before we go, because we haven't really talked about the patterns yet. Alright, quickly look up at the board, because the bell's gonna ring. And if it rings, you're gonna wait until I'm finished, okay? Guys, I can't have you missing this, okay? This is the most important part of the lesson, that you're gonna use this over and over again. Okay. Don't turn around now. That's what's all just to get you guys to turn around and pay attention, so stay here. And if the bell rings, you're gonna chill with me a minute longer, okay? Listen. One thing here that you need to know is that if you're putting stuff away, you're not paying attention. One thing you need to know is that this energy level, if you look at your periodic table, everything, hydrogen and helium, they're in the first row. Everything in the first row is going to have how many energy levels? 1. Everything in the second energy level is going to have how many, everything in the second row is going to have how many energy levels? 2. Everything in the third row, beginning with sodium, then magnesium, aluminum, they're going to all have how many energy levels? 3. And then 4, and then 5, and 6, and so on. That's one pattern. The other pattern, which is extremely cool, so you don't have to draw this every single time. You will for the chart, but in the future you won't have to. You're going to be tested on this next time, Gerd ones. Pay attention. The other thing is that notice here you have 1 valence electron. When you skip down to lithium, you also have 1 valence electron. Guess what? They're both in the same column or group or family. Everything in group 1 right here is going to have 1 valence electron. Everything in the second column, group 2, is going to have 2 valence electrons. These middle elements here are called the transition metals. Their number of valence electrons varies because their electrons travel freely. That's what makes them such good conductors of electricity and of heat. So you can't really determine their valence electrons. But if you get over here to group 13, where it has boron, aluminum, gallium, and so on, then it's 3 electrons. Group 13 is how many valence electrons? 3. Group 14, can you guess? 4. Group 15? 5. And there you have it. Good job. Pack up. You finish your charts. Bring them back Friday, please. Have a good one. Push in your chairs. I'll excuse you by row.